Hello everyone. As you know, today is Pi Day. Pi is found everywhere, especially in fields of mathematics and physics. In this video, I am going to be demonstrating 5 different ways to show pi, both visually and mathematically, using props to derive pi. And so without further ado, let's get started. So for the first example, let's assume that you're going to draw a circle, perfectly round, like this. And you're going to inscribe it in a square, like this. You know, it's not perfect, but it's fine. So, in this example, I'm going to give it a radius, yeah? Just like this. Here we go. And the square also has the same radius, but it's twice as much as the first one, so it has a length of 2r. And we're going to say that the area of this circle in here is equal to pi times r squared, standard formula, and the area for this particular square is going to be equal to twice the radius times 2r, because that's also the length and width given as the square, which was equal to 4r squared. Now the interesting thing about this is that it actually has a ratio of pi over 4, which I'll demonstrate right now. If I do this, you know that it cancels out. You get pi over 4. Which is interesting because you can also see it as like a percentage, like about 78% of this circle is in this particular square. But let's say I made it even bigger for the purpose of our demonstration, and giving it its radius so we can identify it easily, and inscribing the same square like so. And the interesting thing about this is that if we were to randomly pick a random point on this particular circle, or like assume that the random point lands on the circle, that it can actually approximate pi. And I'm going to demonstrate how it actually works if you come along with me right now. And we're going to bring it to the background right now, as you can see it here. Alright, so let's use this spool to help determine how to draw this as quickly as possible. There we go. Just to get to this point. And we'll just do it like this. Okay, right. Alright. And then just draw a circle. Right. Cool. assume that the rest is just a square entirety. There we go. And the rest is 2R. Alright. So I'll be using these strips to simulate those points I'll be throwing on the circle. And there might be some error because it's not some of them might fall outside the circle and it might affect the probability, but I'll try to avoid that. So we have 100 chips and we're going to start doing it now. 25. I'll just randomly throw them. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And we're doing the second set right here. One. Pretty fun actually, but you see it's supposed to converge towards pi over 4 according to the law of large numbers in probability theory, which means that as the number of outcomes increases, it's eventually going to tend towards pi over 4. But you can still use it to simplify if you just rearrange terms. So I'll just continue. Okay, so now that we've distributed all of those 100 chips or points, we can finally find out the probability given all these outcomes have occurred. So if we were to look at how many are outside the circle, 1, 2, 3, 4, 5. So out of 5 that makes 95 have landed in the circle, so it's right here. 95 have landed out of 100. And if we look at that as a, you see like it's supposed to be roughly 0.95, and it's approximately supposed to be equal to pi over 4, but it's above, so it's not really the best approximation. But let's see, if I multiply by 4, what do we get? We get roughly So we get 3.80, which is slightly above 3.14, but it's not all that bad, but it could be improved if we were to use more of these chips, which I currently don't have. But still according to the law of big numbers and probability theory, if we were to increase the sample space, it will roughly equal to pi itself, pi over 4, and then you can rearrange 4 pi. And that's in the first demonstration. Alright, so for our second demonstration, we're going to be drawing a perfectly round circle for this. So I'll just use like so. Right, that should be almost there. Okay. So we've got this round circle, which will give it a radius r and of 1. And then we're also going to say that it has a perimeter of 2 pi r, or circumference. We can also, since the radius is 1, we could say it's 2 pi. And we're also going to insert a polygon to show that we can approximate the value of pi using the polygons, which I'll show now. Okay, so here we're going to draw a hexagon because it's a nice robust shape, and we can start off using it. Just draw sides like this, and we'll just start like that. We'll use equilateral triangles just to avoid confusion. Okay. Okay, we'll just ignore this middle one because we don't want to accidentally create something larger than what we already have. There we go. So that makes 2, 4, 6. 2, 4, 6. All right. Well, I mean, we can ignore some parts like 1, 2. This will just be a bit like this. There we go. This is not the best way to draw it. It's ugly, very ugly, but it will do for now. Okay, sorry about that. And we're going to say that this is R, that's R1, and we want to find its length because that's essentially how you find a perimeter. Whoops. Give it length L. Okay, and given that, we can say that L, we want to find the side length. So we're going to take this and cut into 2 parts, which we can use and we're going to say that because of this, since we're cutting into half like this, which is still a radius but just into 2 parts, we're going to call it A and B for now. There we go. That's nice. Alright. So yeah, we know that A plus B equals 1, and if we want to find the side length, we're just going to use the Pythagoras theorem. So it's kind of straightforward. we're just going to do, the first one we're going to do r squared plus r squared. We're not doing plus, sorry. We're going to make it equal, because that's what it means. A squared plus the side length, which we just chopped into half, squared. That's the first one. And for the second one, we're going to do something that looks a little like this. Okay, sorry about that. Here's something that looks like this. But instead of using R, we're just going to use A. Yeah, that's good. A squared squared Alright, we're just going to use the first formula. This is kind of confusing, so. We'll start with trying to find A. So, A. So we're just rearranging for now. Squared plus 1 minus squared over 4. That's our first one. And if we wanted to find what B is, well, we don't have to worry about this actually. This is just kind of redundant. Okay. Right. And then we know that this is actually an equilateral triangle, so since you know this is the radius, or right here, radius, 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 like that. I'll make it more clear that it's an equilateral triangle, despite the horrible drawing. We'll just ignore that point. We'll just do like this. There. Which means that we already know that the length here is 1. So it actually simplifies greatly. If you know it's 1, you can say that A is equal to this is just which is equal to 3 over 4, and taking square root we just get 3 over 2. Okay, and then over here we can substitute this in. I'll just show you for one of these examples that since we know it's just 1 over 2 squared, we don't have to do all this stuff right here, computations and whatnot. 1 over 4 plus 1 over 2. squared, which is equal to just 1 over 8. And we just take the square root again. And we get something that looks like this. That should be our first edge length. And that shows how to solve the perimeter. And since we're just adding number of sides, we'll just multiply this there. And then up over here, we just divide it here. Here, we get 3 over 2. And that's the first one. So as we can see over here, we'll just use the fact that the perimeter is enclosed in the perimeter circle. So in this case, we know that if the perimeter of the polygon inside the circle is equal to that of the circle, it'll be directly equal to 1. So in this case, we can just rearrange like this. Given that we already know that's equal to 2 pi r. Rearrange again. We get something that looks like this. There you go. But it will be approximately equal and should be approximately equal to pi if we just use different shapes. In this case, we're still using this particular perimeter that's already established. And then we get 3 over 2 over 2, which in this case should be approximately equal to just saying 1.5 times 1 over 1/4, or just simply 0.7 times 2 over 1, and that should be exactly 4. If I over 2, we just take this out, we get 4 times 0.7 times 5. There we go. And 5 over 4, this goes all the way to 1.25 times 1 over 0.7, which should be equal to 7 over 10, so you get 10 over 7. And this should probably, or we can just turn back into 5 over 4 now, actually, you know what? Yeah, okay. And that should give 50 over 28, which should be equal to, if we were to perhaps, well, let's say, take out 20 plus 8. And then also, sorry, I'll just make this fast. 40 plus 10 over 28. And then we get something that looks like this. 40. In fact, we can turn it into something like this. 28, 2, plus 10. This just cancels out, so we get something that looks like this. (22 over 28), which should be approximately equal to, at least, if we were to say 20 over 28 plus 2 over 8, which is 2 whoops, let me just do that. 2 and 28, which I'm now going to greatly simplify. Or at least remove that part, because then I don't exactly know what it is yet. If we have 20 or 28, they're just an approximation, so given that, nearly 0.7. Because it isn't the actual result, so probably just a mistake in here, but it should be approximately equal to 5. But forget about all this. The fact goes that if you were to take the length, you'll get the length of the next polygon, and then you can use the length of that next polygon to find the next one, and so on. And the more polygons you add and create, they'll give you pi if you were to combine all of them into a single shape. So that's probably how to do that demonstration. Okay, so for my next demonstration, I'm going to be using needles to show that pi can be derived by throwing needles randomly on a particular board or anything that looks like this over here. So it's basically something called Buffon's needle, which was formulated a long time ago by the namesake, the person who made it himself, I'm pretty sure. And here's how I'm going to start. I'm going to just randomly drop these. I'll explain how pi is involved. Right, let's just get some more needles. There's scatter a bunch of them right here. And I'll just take this one. Okay, so now we just got. Alright, let's start in that there. Alright, that should do it. And a couple more. Actually, I'll just pour all of them down here. There, that should do it. I'll just pour this last. Okay, so essentially what I'm trying to find is how many of these actually cross those parallel lines that I've drawn, which are twice the length of each toothpick. So so basically the generic formula is 2 times the number of crossings over the ones that actually land on the lines here. And to simplify this, I'm going to be using a calculator for this. So let's see. And these number of crossings should be approximately equal to pi. So let's see. We have, just had to look at the lines, we don't have to worry about anything else. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 have crossed over there. And if we were to use the 20, 21, 22. Okay, so if we're supposed to exactly approximate pi than we are to use a number of crossings. We have 20 that have fallen and have landed exactly on these lines here. So if we were to look at number of crossings and number of toothpicks that just fell off, that's the covering we have here. I'd say about 100. So we'll just go with that. Approximately 2 times. I'll just fix it. There we go. 40. Back. Alright, so we have the number of crossings, the total number of drops, 100, so 200 divided by 20. 200 divided by 20 should give about 200 by 20. Alright. It should give about 10. But that would make sense if we were to do that. Let's see. 2 times, yeah, 200. Sorry, calculating there. Yeah, it can't be 100. So we're gonna say that it's not gonna be 100. So let's decrease that to. Maybe I should probably draw it right here. Yeah, that's a good idea. So pi should be approximately equal to 2 times the total number that dropped. What x number of crossings across these parallel lines over here. So let me just do this. If it's not going to be 100, then we'll just decrease it to 50. Uh, 50 into 20. Which should be probably 5. Yeah, 5. And these may not be enough needles, actually. So what if we were to use something like, if it's not 20, let's look at how many we have over here. Let's see. Okay, well, let's just decrease it to 20 because we don't actually have 100. It's probably not 100, so 40. Yeah, 40, because then we'll just say we have 20 of them for 20, which means that about 2 have dropped, which isn't so bad, but we need more in order to, we need to drop more needles in order to get to pi. Just like the first example, where we need more of those points in order to approximate pi, but we don't have them right now. But it still approaches pi nevertheless. Just like the law of big numbers, if we were to use that in probability, it would still approach pi. So there you go. In this example, I am pouring these rice pellets to show that it forms the area of pi via the Gaussian integral. Because once I pour it in the actual tray, it actually forms something that resembles a Gaussian integral, and that also shows how pi can be shown in nature. For the last example, when you create a vortex ring in water, the swirling motion follows circular paths. The strength of this vortex, how fast it spins, is linked to pi through the math of circulation. Essentially, the way fluids naturally form and sustain vortices involves pi, just like circles do in geometry.